This video addresses a common problem in how calculus is often taught, namely the early emphasis on limits. Limits are an important tool used to rigorously understand calculus, but a long time in a course is spent computing limits, because in order to compute derivatives, you have to be able to compute a bunch of limits, right? Well, this naturally begs the question, what is the fewest number of limits needed to compute derivatives? My answer boils down to those needed to compute just 5 derivatives, and the 10 or so limits that they do need could be used to teach about the properties of limits. In short, I propose that derivatives should be used to teach limits, not the other way around. Not to bury the lead, but these are the 5 derivatives we need limits for: the identity, the chain rule, linearity, the exponential, and sine. These 5 reveal much about the derivative and its properties. First, we have the derivative of x, or the identity rule. The limit argument is so simple that it boils down to the limit of a constant being constant. Why is this one so important? First, it tells us when a derivative gives us a number, it refers to some rate of change. Here in its simplest form, this formula tells us that the output changes identically with the input. Secondly, it is necessary to terminate other computations. Otherwise, we would run into an infinite regress when we use our second rule, the chain rule. This limit argument presented is not completely rigorous, but this sketch presents the key idea in understanding how we get to the chain rule. It tells us that between changes in cause and changes in effect, we must account for the change of each intermediate effect in turn, and multiply all of these together. After these, the next most important rule is the derivative's linearity, where constants pass through the derivative, and the derivative of a sum is the sum of derivatives. This fact is important in and of itself, but if you've ever heard of a class called linear algebra, it precisely deals with objects that satisfy this rule, and all of the consequences therein of being linear. One of the consequences can be seen in the next rule, the exponential, also written e to the x. In linear algebra terms, it is the eigenfunction of the derivative with eigenvalue 1, which ultimately leads to the entire content of some differential equations classes. Even if linear algebra is not important in your future, this rule is super important in a lot of calculus classes because of the rule exp of x plus h is equal to exp of x times exp of h, which will generate a lot of rules for us. Finally, we have sine of x. This rule is probably the least important, but it gives us all of the other trigonometric functions, and we'll also see by the end of the video that this can give us Euler's identity. It also reveals that the derivative applies some manner of phase shift to a function, and it teases out a potential avenue towards fractional derivatives. But that's for another video. Its limit argument can also teach a lot of important ideas about limits, on the ways such as the squeeze theorem can be applied, and can be taught to enforce the notion that the limit serves the derivative, not the other way around. Now you might be surprised that a bunch of other rules didn't make the list. Like, where is that disgusting thing called the quotient rule? But if we take these 5 derivatives on their own terms, we can get almost all of the other famous rules. To do so, we'll need to be comfortable applying all of these rules. For example, we can find other eigenfunctions of the derivative by considering the exponential of lambda x, which uses the chain rule, the exponential rule, linearity, and the identity rule to get the following derivative. The first step on our journey is probably the strangest, where we apply a chain rule with a logarithm on the outside. Since the logarithm is the inverse of the exponential, we can rewrite the equation as an exponential one, which is easy to differentiate, and then to solve for the derivative of our original function. Use of a logarithm is very important, because if we have some generic product, applying the logarithm to our equation allows us to turn the logarithm of a product into a weighted sum of logarithms, allowing for linearity to swoop in and clean up the rest. In addition to the classic product, quotient, and power rules, it also allows for an easy generalization of them, known as logarithmic differentiation. One simple example of this is the constant function, which we can treat as x to the 0th power. Applying the power rule tells us that the derivative of a constant is 0, which in turn says that a constant never changes. Finally, the remaining trig functions are built off of sine of x. Cosine of x can be written as a phase shift in sine, differentiated, and then phased back to get negative sine. From there, the other trig functions are simple products and quotients of these. As an exercise, find the derivatives of each of these using logarithmic differentiation. As a final example, we'll show Euler's formula to be true using our rules. To motivate Euler's formula, we'll observe that the second derivative of sine, cosine, and the exponential of k of x are plus or minus k squared times the original. All 3 would match if the trig functions used plus or minus 1, and if the exponential used plus or minus I, with I squared being equal to -1 by definition. This is enough to suspect a relationship between them. So we take a linear combination of the trig functions and divide it by the imaginary exponential, which gives us the function f of t. Using logarithmic differentiation, the rules for cosine, and our eigenfunction that we derived from the big five, we find that the derivative of f is 0 everywhere. We have the benefit of hindsight to know exactly which linear combination of sine and cosine would work, but we could have done this with a generic linear combination and then determined workable coefficients. If a derivative gives a number, it is saying something specifically about a rate of change. And specifically here, it means that the derivative is 0, there is no change. And since t was not specified, this is true everywhere. A function that does not change anywhere is constant. Which constant is it? Well, we can just evaluate at t equals 0 and find that this ratio is 1, which means that the top and bottom are equal for all t. This gives us that the exponential of it equals cosine of t plus I sine of t. What all this goes to show is that while limits are needed to formally define derivatives, derivatives can reveal themselves pretty handily on their own terms. In fact, if you memorize these 5 rules, you can get all the other common derivatives without reference to limits at all. If you've taken calculus before, I hope this taught you something new about how to understand derivatives. If you have not, I hope this video doesn't scare you away from calculus. And if you like this video, then please like this video.